In the last video, I had you do that Coulomb's law problem, and we actually did it the hard way. Okay, so the reason I had you do that is because I wanted you to develop an appreciation for the unit vector. You may have seen this before, but I'm assuming that you have forgotten most of it by now. So we are going to rework that same problem, but using unit vectors, and I think it will give you an appreciation for them. When I first learned about unit vectors, I thought that they were stupid. I really did. I thought that it was just way easier to just use trigonometry. It was something that was intuitive to me, and and adding all this unit vector stuff was just like complicating stuff. But over time, I changed my mind, and hopefully this example that I'm going to give will change yours as well. Okay, so what is a unit vector? So remember in the previous problem, we had to calculate the magnitude of the force, and then we had to do like a bunch of trigonometry and looking at angles and things like that in order to determine the x and y components of our vectors. Well, we don't actually have to go through all of that mess. Turns out a unit vector is it's a type of vector that allows you to easily determine the components of a force, or it can be any quantity. We'll also do it with electric fields. When you know the magnitude of the force here. So if we know the magnitude, we can, and we know the unit vector as well, then we can easily use it to figure out the x and y components. So specifically, we can say that a force F, or a vector F, this little arrow here indicates a vector, can be represented in terms of its magnitude. So this means magnitude, these little bars here, and its magnitude times the unit vector here. We call it F hat. Basically, if you put a little hat there, it means that it is a unit vector. So what this is saying is that if you know the magnitude of the force, all you have to do is multiply the magnitude of that times its unit vector to figure out the full vector with all its different x, y, and z components.
Hey, Miwa, you like that vent? Yeah? It's nice and warm? Yeah, it's nice and warm. Uh-huh. Yeah. Oh, yeah. Oh.
Okay, so I defined a unit vector in terms of like what it does, but what is the precise definition mathematically? Well, one, not surprising, is that a unit vector has a magnitude of 1, or unity. And secondly, a unit vector always points in the same direction as the force, or any other vector quantity, that it is representing. There are two types of unit vectors. One is the coordinate system unit vectors, or what we call the base vectors. So for example, if you have a Cartesian coordinate system here, x, y, and z, this is three-dimensional here, basically you can say that we have unit vectors. The unit vector in the x direction is called x hat. It has a magnitude of 1, and it's in the x direction. In the same way, we have a unit vector z hat that's in line with the z-axis here, and it has magnitude of 1. But in addition to the base unit vectors that we work with, we also work with any arbitrary unit vector. So any vector that's in this coordinate system that can have that has a magnitude of 1 is a unit vector, but typically we express it, or we represent it by a sum of base vectors. So for example, you could draw literally like any arbitrary vector in this coordinate system, and it'll have a certain magnitude, or I'm sorry, it'll have a magnitude of 1 if it's a unit vector. So let's call this like f hat. as some random unit vector here. But the thing is, though, it's not oriented perfectly in the x direction, the y direction, or the z direction. It has a piece of both. So we can actually represent this f hat with something like this. Basically, it has a certain amount in the x direction, so we say x hat direction, a certain amount in the y direction, and a certain amount in the z direction. And basically this whole thing, if you take the magnitude of this whole thing, it should be equal to 1. And by the way, I'll just mention the magnitude here would just be the square root of all of these squared. Okay, so if you're still just maybe a little bit confused on what a unit vector is or how it all works, I think the best thing is just to dive straight into an example here. And we can use unit vectors with Coulomb's law. So here's Coulomb's law, but in, you could say, formal like unit vector um, notation here. So we have still, our two charges, Q1 and Q2, separated by this distance, but then we define a unit vector here, R12 hat, going from 1 to 2. And what Coulomb's law says is that this vector here, F21, the force on charge 2, is equal to r hat 1, 2. So the unit vector going from 1 to 2 times our whole expression here. And when you use Coulomb's law in this unit vector sort of form, you'll see in just a minute that it really simplifies our problem greatly. All right, so we're going to go ahead and do the same problem we started with in the last video. For us to be able to use the unit vector form of Coulomb's law, we have to find out what are the unit vectors for these forces that we want to calculate. So we need to find out what is the unit vector from 3 to 2, and what is the unit vector from 1 to 2. So the unit vector from 1 to 2 is equal to this. So let me walk you through how I calculated this. All right, so the unit vector from 1 to 2 is a vector that's in this direction that has a magnitude of 1. Let's first focus on the direction part of it. We know that going from 1 to 2, it shifts -1 in the x direction, and it shifts +5 in the y direction. So therefore, you can represent the direction of the vector, of a unit vector here from 1 to 2, as -1 in the x hat direction, right, plus +5 in the y hat direction. Now, this gives us a vector in the direction we're looking for from 1 to 2, but it does not give us a magnitude of 1. So what you have to do is you have to divide this whole thing by the square root of the magnitude of this. And this will give us a vector that has a magnitude of 1 that's in that direction. So that is r hat 1, 2. So then you just plug and chug there and you get those numbers. In a very similar way, r hat 3, 2, here going from 3 to 2, you can see you shift +4 here, and then +2 in the y direction. And so there's our vector there, the orientation there, but then you have to divide it by the magnitude to get that unity magnitude. And so then you just plug and chug, and this is what I get for the two unit vectors. Okay, so the rest actually is super straightforward now. Literally, to find out what the total force is, all you have to do now is just add these two forces together, and it's literally like a plug and chug, F21, F23, but in the unit vector form that we saw. So basically, you take your calculated value for r hat 1, 2, multiply it times this whole expression, which we calculated that expression in the last video, so I'm not going to plug those in or show that explicitly. But basically, you plug and chug these unit vector values that we got there. And then, of course, you do your algebra, distribute this term, and also then eventually you'd add these x hat parts together, add the y hats parts together, And you combine that, and I get this. This is minus 13.41 x hat plus 0.75 y hat millinewtons. This is the x part of the force. This is the y part of the force on charge 2. And these are the values we calculated in the last video. See how much easier that was? I mean, it was literally just like so systematic. We just plug and chug. And then if you want to find the magnitude, you just take the square root there. 13.44 millinewtons, which is what we calculated in the last video. So I hope that gives you an appreciation for unit vectors, and we certainly will continue to work on this. There are different kinds of coordinate systems that we can talk about, and we definitely will be working more examples. Another thing I want to mention just as an aside is I haven't been talking a whole lot about like the physics behind stuff. I've been just kind of like just giving you formulas and kind of jumping into the math, and that's kind of intentional just to kind of get your feet wet, to review some of these mathematics. But after going through some examples, we're going to kind of take a step back and really try to develop a better intuitive understanding and try to delve more into some of the practical, like real world sorts of cases of these things. So thanks for watching, and I'll see you in the next video.